gentlemen, welcome to our second session, second speaker, and also our last speaker for today of our IMO showcase problems. It is my great pleasure to introduce to you one of our instructors, Qiang Shen. Qiang Shen is a very well-known teacher, especially in this northeastern part of China. He's been with us as an instructor starting last year, so let's give him a welcome.
Well, in fact, I think that the polygon problem is too difficult for me. I don't think I can solve that problem by myself. But the problem I present is a rather easy one, because it's the first problem from the year 1996. But I did not prepare any documents, so I'll write it out manually. Okay. If I remember correctly, it's a chessboard. That's a 12 by 20 chessboard. Do you remember this problem? Does anyone remember this problem? On a 12 by 20 chessboard, and a piece jumps on the chessboard according to a certain rule. Okay. Well, the problem states that R is a given positive integer. And the piece can jump from one square to another square, if and only if the distance between the centers of the squares equals the square root of R. For example, the regular knight, the R is 5. Okay. So the first part is rather easy, but I'll present it in a twisted way. So let me define a type of piece, which is called the MN knight. Okay. So here, M and N are distinct positive integers. And this piece moves M squares to one direction, and N squares to a direction perpendicular to it. So the regular knight is a 1-2 knight. Okay. Now, suppose that the chessboard is infinitely large. Okay. If the chessboard is infinitely large, then for what values of M and N can this piece reach every square? Okay. I mean that this piece can go from any square to any other square. I don't mean any thing like Hamiltonian cycles. I only say that the infinite chessboard is connected with the MN knight move. Okay. Do you think this is well known? For what values of M and N is the infinite chessboard connected? I only ask for connectivity. Co-prime, co-prime. But is co-prime enough? coprime and yes, coprime and n plus n is odd. Okay, so it's obviously necessary. Can you prove that it is also sufficient? Well, I think this is seen somewhere else. Do you remember? Where have you seen these conditions? Somewhere else. Somewhere else. Okay. Do you remember the formula for primitive Pythagorean triples? M squared minus n squared, 2mn, and m squared plus n squared, right? Okay, and for this triple to be primitive, we need exactly these conditions, right? Okay. Now, it's obvious that if any two of these three numbers are coprime, then they are pairwise coprime. So we make use of the fact of this Pythagorean triple being primitive. Okay, so from 0, 0, we can reach m squared and mn. And then, from this, we can reach m squared plus n squared 2mn. Okay. Well, we also change this to 0, right? Okay. But we can also reach m squared minus n squared 0. Okay. So, since these numbers are coprime, with these moves, we can reach 1, 0. And therefore, you can move to an adjacent square. So this proves that these conditions are also sufficient. But this is the case for the infinitely large square. Okay. Something may be different if the chessboard is finitely large. Okay. So you see, the original problem asks for 97. Okay. You see, 97 is prime. That is 1 mod 4, and therefore, this corresponds to uniquely to a knight. Okay, In this case, it's a 499. 499. 499. Okay. Also, it is a 12 by 20 chessboard, but the problem asks you to move from one corner square to another corner square, which is, in fact, moving 19 squares long, not 20 squares long. You move them by 19 squares. Well, I think that on many books that has this problem, they give a coloring, but very few books gave reasoning of how to construct that coloring. Does anybody remember that coloring? Well, it seems to be like this. Divided into 1 by 4 parts. And color them alternately black and white. Then, the 499 can only ever jump to squares with the same color. But the original problem wants us to jump from a black square to a white square. Okay. So, I'll tell you what is really behind this. Well, so let's consider the original problem. So now let's assume that the chessboard has only infinitely many rows, but infinitely many columns. Now, to make these moves, how many rows do we need? Okay, so you see, when moving from 0, 0 to m squared mn, you moved up by n rows for m times. Then, when moving from this to this, you moved down by m rows for n times. So how many rows do we need? Note that we can make these moves in any order. We don't need to begin moving down after moving up for mn rows. So how many rows do we need? Well, this structure reminds us of an even earlier IMO problem. Well, do you remember that even earlier IMO problem? Suppose you have a sequence. Okay, so the sum of every m consecutive terms is positive. But the sum of n consecutive terms is negative. Here, m and n are still co-prime. Then what is the maximum amount of terms? I think you remember this, right? So what is the answer? What? M plus m minus 1? No. What is it? What is it? What? So yes, this is an even earlier IMO problem. So what is the answer? It's obvious that if there are n plus n minus 1 terms, there's a contradiction. You just make an array like this, right? You make this rectangular table. Okay. Then the sum of each row is positive, but the sum of each column is negative. Well, so does m plus n minus 2 work? Wait. It indeed works. Because you can write out the partial sums. Okay. The partial sums. Okay. S1, S2 are up to Sm plus m minus 2. Okay. Then let's see what the restrictions can be. Okay. So S0, oh, this is, so S0 is 0. So S0 is smaller than Sm, but larger than Sn. Then you write them out. The indices either increases by m or decreases by n. Then all the numbers from S0 through Sm plus m minus 2 form a chain. So what is the last member of this chain? Well, it should be Sm minus 1, right? From here, you can't go any further from here on. Okay, so you can always assign values to the partial sums because they form a chain. But if there's one more term, then they form a cycle, which is a contradiction. You see, m minus 1 is smaller than Sm plus m minus 1, which is in turn smaller than Sm minus 1. Okay. So this is a construction of m plus n minus 2 terms. Also, let's take a look at the indices. You see, two numbers from 0 through m plus n minus 2 differ by m or n, if and only if they are adjacent in this sequence. Okay, so these are m plus n minus 1 numbers. Now, we label each row for example, from bottom to top, row 0, row 1, until row m plus n minus 2. Okay. Then the rows are in a sequence. Okay. Now, color the rows alternatingly blue and red. Okay. Then you see, the knight can only jump from a blue row to a red row, and from a red row to a blue row. Okay. But if you look at the usual coloring of the chessboard, it can only jump from a black square to a white square, and from a white square to a black square. And therefore, if it starts in a white square in a blue row, then it jumps to from a white square blue row. Okay, white square blue row. Then it can only reach a black square of a red row. And then return to a white square of a blue row. It can never reach a white square of a red row or a black square of a blue row. Okay. So these two parts are disconnected. Okay. And therefore, the reasoning is that if you consider this as a graph, so this graph is a chain, and a chain must be a tree, and every tree is bipartite. But if you add another row, then it closes up to a cycle, and this cycle is odd, and the graph is no longer bipartite. Okay, so this is the problem. Okay, so any more questions? Okay. Okay. So I don't have anything more.
Okay, let's thank Qiang for a great talk. And now questions. Any questions, please? Raise your hand so that I can see you. Any questions, please? Don't be shy.
Well, maybe this is just since this is just a problem one, there's
What year is this from?
what?
What year?
1996. Or maybe 1995, I don't remember it very clearly. Okay.
Any other questions? No other questions? If there are no other questions,